guys, Miss Kulkarni here. In this video, let's talk about isomers in organic chemistry. And our main focus is going to be on chiral compounds. These chiral compounds are extremely important in organic chemistry and also in medicinal chemistry. So, what are isomers? This is a chart which explains how isomers are classified. So we got main branches of isomer as called as constitutional, or we also use the simple word structural isomers, and the second one is stereoisomer. Stereoisomers are the ones which are further branched to configurational and conformational, and of course we get more branches of the configurational isomers. Now we will talk about each of the branch later on, but the focus of this video is going to be on chiral compounds, and that is enantiomers, which is right over here. So before that, let's find out what are isomers. Isomers are different compounds. They are not the same compound, they are different compounds with the same molecular formula. Now, the two major classes, as we saw in the table, are these two. One is called as structural isomers and the other one is called as stereoisomer. Structural isomers have totally different IUPAC name. It may have same or it may have different functional groups. One may be ether, one may be alcohol, and they could be still isomers. And they can have different physical properties and chemical properties. So that's about structural isomer. Stereoisomers is our focus. So these are the one in which the main thing is the atoms are oriented in space in different manner. So it is just like seating chart. If the seating chart is different, then the molecules will have isomeric structure. And we have same name for the molecules, but there's a prefix could be different. We can have cis or trans or E or Z or S and R. So they all will also have exactly same functional groups. Just to explain a little bit, here is a quick differentiation between our structural isomers and stereoisomer. So look at this first compound. This is, if you look at the carbon chain, that's 5-membered. So this is pentane, and if you look here, that's also 5-membered. So we got this as pentane. But this says 2-methyl and this says 3-methyl. Why is that? There is a methyl group attached as a substituent, and if you number these, then this is attached to second carbon, whereas this is attached to carbon number 3. So this becomes 2-methyl pentane and this becomes 3-methyl pentane. The molecular formula is same, but look at that. It has got two different structures. That is about structural isomer. The stereoisomer, the example here is about cis and trans. So if you focus on this particular carbon atom here, the methyl group is showing as if it's popping out of the paper, whereas this is going inside the paper. That kind of tells you the orientation is different for that. Now again, our focus is going to be in all of this is going to be on enantiomers. And before we look at the structure, I want to just tell you, we will be able to identify the stereo center or chiral center when you're done with this video. Don't you believe me? Yes, I'm going to show that to you. Just one simple note. It has a big impact in medicinal chemistry. So there was a medicine which is called thalidomide, and I'm using the word Thalidomide Tragedy. This was a medicine which was prescribed to pregnant women to help them with morning sickness, to prevent them from morning sickness. And thalidomide has two different isomers, and these isomers were not separated, not purified. So when these pregnant women took the medicine, they got the effect of both the isomers. One of the isomer was doing what it's supposed to do, working as a sedative, but the other one was causing some dangerous side effects. And we'll talk about the side effects when we discuss thalidomide. So it was very important to find out what the isomers are. So let's get to our optical isomerism, or which are enantiomers, and the chiral center. All these are going to be same things. So everything which we see in universe, if you put in front of the mirror, you're going to see a mirror image. So they will have a mirror image, of course, but the mirror image may or may not be superimposable. Now take the example of hands. Your left hand and right hand. If you imagine there is a mirror in between your left and right hand, your right hand appears as if it's a mirror image of left hand. Now try to put both these hands together as it is shown in this picture. Can you superimpose those? Nope. You can never match the thumb which we have for your one hand with the thumb on the other hand. So that means they are not superimposable. Let's look at some other example. These are pair of socks, and I know I put my socks in laundry, and when I fold, I don't care as long as they are matching. So socks are mirror images too. It doesn't really matter the left and right sock, whichever foot I'm going to put into, unless the socks have the toes. Some socks come with the toes. In this case, they don't come with the toes. So the simple socks, they will be exactly same. They will be mirror images of each other, and I can superimpose that. So in this case, we are going to call these as achiral. If the image of a molecule can be superimposed, that's achiral. And if the mirror image is not superimposable, then that's called as the chiral center or chiral molecule. You're already getting the point. Here is the example of the real molecules. Look at the first one. That's water. This red ball which we have is oxygen, and these two are hydrogen. So if you look at the mirror image for water, and then if you try to take those both images and try to superimpose, what do you get? You can get both of them exactly matching. That means water molecule is not a chiral molecule, it's called as a chiral molecule. How about the second example? This is CH2BrCl. So this is carbon. These white balls are called as hydrogen, and let's label maybe red as chlorine and green as bromine. So this is same way. This is hydrogen, red is chlorine, and this is bromine. So I got this as a mirror image. Well, can I superimpose? You may think in the beginning you cannot superimpose, but you know what? If you twist the molecule around, you can easily match both these hydrogen atoms, and they can be superimposed. That means even this molecule is achiral. Now I do want to note one more thing here. We got here carbon, and to that carbon we got two atoms which are similar atoms, hydrogen. Same way here, this is oxygen. We got two atoms which are similar atoms, hydrogen. So let's see the other molecule, and we'll come back to this. So this is about a chiral molecule example. And there are two examples given for CHBrClF. So this is your carbon, and then the red is going to be chlorine. Let's make that green as bromine, which you had, and then this orange is going to be fluorine. And then we look at the mirror image. So if you take that mirror image and try to superimpose, you are never ever going to superimpose that. Okay, now look at the carbon which you got. Each atom which is connected to carbon is different. This is hydrogen, this is bromine, chlorine, and fluorine. So what does it tell you? The molecule is chiral when the carbon atom is connected to all four different atoms. See, we are getting close to our answer. Now, this is another example which I am showing you with the two different molecules which we talked about. This was CH2BrCl and this was CHBrClF. So over here, what happened was we could superimpose these. Look at that. There are two hydrogen atoms here because there is a plane of symmetry. When I construct the models, I can easily have a plane of symmetry. Whereas when we look at the second molecule, it only got one hydrogen and each of the atom, the remaining atom is different. I do not see any plane of symmetry for this one. So you're getting close again to some clues. If the molecule has a plane of symmetry, is going to be a chiral molecule. If the molecule has no plane of symmetry, is going to be a chiral molecule. So are we ready to find out some chiral centers from these molecules? This is nicotine molecule. And look at this carbon atom which we got right over here. That carbon atom is linked to 4 different substituents. Yes, they are all 4 different substituents. You can see 2 of those clearly. One is hydrogen. Second is this big ring. The third and fourth are part of the ring. The ring which we got over here, if you go in clockwise direction versus we go anti-clockwise direction, those act as 2 different substituents. So, since the carbon atom has 4 different substituents, what did we come up with? It is going to be a chiral molecule. And this carbon which we got will be the chiral center. Let's look at the next one. This is norepinephrine. And do you see a chiral center? Yes. So look at the carbon atom which we got over here. Now not all of the atoms are shown there. There is also one hydrogen which is there. So now the carbon atom got hydrogen, and then we got this ring on as a second substituent. We got hydroxide as the third substituent, and of course this group, amino group, as the fourth substituent. So that means it will be also a chiral substance, and that will make a chiral center there. So this molecule here is thyroxine. Can you find out the chiral center in this molecule? Look carefully. Did you find it? Well, let me show you where is the chiral center. It's right over here. So this carbon has got couple of groups attached to it. One of them is of course simple hydrogen atom. Then we got NH2, which is amino group. Then we got the third group, which is COOH, and what is it called? It is the carboxylic acid group. And we of course got this big ring attached as a fourth group. So basically it has got 4 different groups, and that makes it a chiral compound, and that is the chiral carbon which we got there. So let's go back to our thalidomide, the compound which we talked about earlier, which caused a big tragedy. So these are 2 different isomers of thalidomide, and I'm telling right now they both have a chiral carbon. See if you can spot the chiral carbon. The chiral carbon is connected of course to 4 different groups, and that's why they have different spatial arrangement, and that gives rise to the 2 enantiomers. So this is the one which is the chiral carbon. And there's one more thing. There is hydrogen which is not shown in the compound structure. Normally we may or may not want to show hydrogen in the compound. It's understood. So now look at the carbon carefully, and you can see there are 4 different groups bonded to that carbon atom. So both the compounds have same groups attached to carbon atom. So what is the difference? The main difference is the groups are arranged differently. So it is the spatial arrangement of those substituent groups that makes it a big difference. These compounds will not be superimposable. That means they will not have a plane of symmetry, and that means they will be chiral molecules. So guys, I hope you understood the chiral compounds and how to identify the chiral center. These are extremely important in medicinal chemistry, and we will talk more about how to synthesize these chiral compounds. What are the challenges to separate, purify these compounds? Okay, I hope you guys enjoyed the video. I'll see you again in next video. Until then, bye bye.